So, now we start today, we will do lot more of what we have seen so far. We will so what I have done in the previous till now is to give you a glimpse of all that we are going to teach in this course till the last so till session 55 or 52, right. We are in session 15. The next 20-30 sessions, what we are going to do, I have given a nutshell. So, we are going to talk about segmentation, we are going to implement segmentation tomorrow. We are going to talk about paging, we are implementing paging, we are going to talk about task switching, we are going to implement task switching, we are going to talk about interrupt service routine, we are going to implement interrupt service routine, right. So, all the basic things that are necessary to have some understanding of this I have covered. Now, what I am going to do next is I am going to do a deep dive into each one of these topics. So, today we will have a more in depth understanding in this session about memory segmentation, specifically segment descriptors. We will have a better understanding of the segment descriptors, right. So, the segment descriptors came into existence right from 8386 and above, and it actually stores some of the attributes of the segment, namely base, limit, privilege, etc. Please note that whatever dada I am, whatever privilege level I am, I will not be allowed to access memory without having a proper segment, and that is one fundamental strength of the Intel architecture. If I want to access memory, it should be defined as a part of some segment, and there should be a privilege level associated with it, and all the checks that are needed to go. However big I may be the real kernel or the micro kernel or the nano kernel inside, I may be the super boss there, but the moment segmentation is evoked, everything has to go through this particular segmentation principle, and segmentation is there by default in the protected mode. I can't have a protected mode without segmentation, and that makes development on the Intel architecture and the AMD architectures very interesting. So, what are all the different types of segments? What is a segment? Segment is actually an area of memory that is defined by the programmer, and it can be used for different purpose to store different things. Depending upon what is stored, the segment is basically called a code segment or a data segment or a stack segment. Please note that segments are not all the same size, they need not be paragraph wise aligned, right, and on the segments I could have 64 kilobytes of segments. Okay. The number of segments that I could have can be up to 64 kilobytes. Why 64 kilobytes? 2 power
16.
2 power 16 is 64 kilobytes, okay, right. So, the total amount of, so why it is 64 kilobyte segments? Are you watching this? So, this is 8386 we are starting off, okay. Okay. Now, this can go up to, the segment size can go up to even 4 GB, okay. It can go up to 4 GB today, okay. So, we are talking of the old segment sizes in real mode 8386, okay. So, this is where people started before protected mode. When 8386 was executing in its real mode, we started something called real mode, which we will not now discuss, that it is meaningless, because when we start we need to have a legacy of x86 itself can be a course by itself. So, we will not go into that detail, because it is not useful as of now, but the old segments, real mode segments, they were of 64 KB size, maximum 64 KB. But now things have changed, and this is now the structure of every descriptor. We had gone through this in great detail so some of the things that we need to keep is the granularity bit, right. When it is 0, the segment limit is measured in bytes. When it is 1, the segment limit is measured in 4 KB pages. Okay. And then there is a descriptor privilege level which we need to understand. Okay. So what does the segment descriptor do? It describes a segment, and for every segment that I am using I need to have a segment descriptor, and it is created by the actually not by the programmer, in the sense it is created by the operating system, not by the architecture, and it determines a segment base address. There are 32 bits, bits 16 to 39 and 56 to 63, because it is totally 0 to 63 bit architecture, bit segment description. It also determines a segment size by 20 bits, which is 0 to 15 and 48 to 51. It also defines whether a segment is a system segment, that is 0, or a non-system segment, that is user segment, which is code, data, stack, and that is called system bit, bit 44. 1 means non-system, 0 means system. It also determines a segment's use/type. There are 3 bits. We will see what those 3 bits stand for. This is type of segment, and there is a it also determines a segment's privilege level. There is 2 bits, bits 45, 46, which talk about the descriptor privilege level, right, DPL. Then there is an accessed bit. As I told you, whenever the segment is accessed, accessed means read or written to, it is set by the processor that it is accessed, and this can be used for by the operating system to do some more analysis of the data, how frequently something is accessed, etc. Then there is a present bit. As I told you, every not fully filled table should have a present bit to distinguish between valid and invalid entries. So there is a present bit here. And then there is bits 40 to 47 of the descriptor. These are called as access rate byte, right. Then we will see what is that access rate byte also shortly. Then there is a user bit and X bit. Bit 52 is the user bit, it is not used, and bit 53 is a X bit, it is reserved by Intel. Then there is a default size D bit, bit 54. When this bit is cleared, that means operands containing within this segment are assumed to be 16 bits in size. When it is set, operands are assumed to be 32 bits in size. So this is very useful in a code segment. When I compile a program for 16 bit, right, then I make the code segment to have a D value as 0 here, okay. That means a 16 bit code. When I make it 1, then it becomes a 32 bit code, correct. So this is very, very important for me to execute legacy codes in this new setup. It becomes extremely important. Then there is a granularity or G bit, bit 55. When this bit is cleared, the 20 bit limit field is assumed to be measured in units of 1 byte. If it is set, the limit field is in units of 4096 bytes. This is a granularity bit. So I could have a segment which is as small as 0 bytes, but 1 megabyte, with the limit as low as 1 megabyte or to as high as 4 gigabytes. Now we will go to the type of the segments. This is S equal to 1 means they are non-system segment or user segment. So if I put the type as 000, it is data read only. 001, it is data read write. 010 is stack expand down read only. We will now explain what is stack expand down and expand up. 011 stack expand down read write. 100 is the code execute only. 101 is the code execute with read. 110 is called a confirming code execute only. 111 is confirming code, execute read. What is confirming code we need to explain, I will explain you down the line, and what is stack expand down, expand up, we need to read that also. We need to specify that. I will do it over the next few lectures. So there is a type bit in this segment, as you see byte number bits number 8 to 11 on the top. That type bit is filled with these values for the different stacks. So for a code segment d equal to 0, then it is a 16-bit 8286 code, as I told you. If your d equal to 1, then 32-bit 8386 code. For a stack segment, if your d is equal to 0, then stack operations are 16-bit wide. So it uses only SP, not the ESP. SP is the 16-bit version. When d equal to 1, then the stack operations are 32-bit wide. So ESP is used as a stack pointer, and you can go up to 4 GB of stack. Okay. So these are the these are the things that we need to understand. And g equal to 0, then a limit field in descriptor of value p indicates we can access p minus 1 bytes from base. G equal to 1 means then it is p into 4096 bytes, the limit. Okay. Now what is expand down and expand up segments? When a stack is expand down, then all offsets must be greater than limit. In stack descriptor, d and g bits are to be the same, else contradiction. Okay. So if I go and see a stack descriptor, the d and g bits have to be the same. Right. So in a expand down stack, what happens? I fix a limit okay. So your base is between, so your base is here, this is the limit. If it is a expand down stack, your thing would be limit FF to that limit will be the addressable area. Right. So limit and above is expand down, limit and below it is expand up. You are getting this? So okay. So this is how we can have stacks. And why do we need stack? Because I will say it is very easy for me to say, right, you go and expand in this area. I can put a limit and say use beyond that limit, and that is much more easy for me to say rather than putting two limits and limit and a limit, and then, so if I say use everything above that limit, then it becomes easy for us to maintain a stack. So that is why the reason expand up and expand down stack segments have come. Okay. So to look at into all these things, what we have done so far is that we have just understood in this part of the lecture some of the important things about the segment descriptors. Some understanding, a deeper understanding of the different fields that you see in this segment descriptor, and that is what we have finally got to in this session.